Dang. I hate when I do that. Well, so if you're watching this on YouTube, I forgot to hit record, so you missed my review. I did a review on this, and you just have to suck it up and take the loss, I guess. I apologize for that. Whoever mentioned that, thank you for telling me to hit the record button. If you just tuned in on YouTube, what we said was two things that what's true for resistors and current is true for capacitors and charge. So I drew this on the board showing that if I have resistors in series, if I know the current going into that series circuit, then I know the current everywhere. The current will be the same everywhere in this series circuit. Well, that's true of charge and capacitors. If I have capacitors in series, if I know the charge anywhere, I know the charge everywhere. So if I'm telling you C1 has 1.5 microcoulombs, that means C2 has the same amount of charge, C3, all the capacitors have the same amount of charge if they're in series. And the other thing that you missed, if you're coming in on YouTube, is I went over the formulas that you can go to the last video that we looked at. We said that capacitors in series behave like resistors in parallel. So the formula I would use for capacitors in series is similar to a parallel resistor formula. And capacitors in parallel behave like resistors in series. You just add them up. So if you missed the review, you can just go to the other video before this and you can look at that. Now what I want to do is I want to solve this problem. And how do you approach a problem with capacitors if I have a DC source? Remember, we started talking about AC, guys, AC, and I jumped to DC because I want to show you how capacitors behave in the DC circuit, and then we're going to switch right back to AC, and you're going to see that they're totally different in the AC circuit. But this is a good place to talk about capacitors in general. So we'll come back to the AC probably after this lecture. Or maybe I might have one more topic and then we'll do it. But here's the point. Given a problem with all capacitors in a DC circuit, whether series or parallel, the way you solve it is by asking this question. If I had all resistors, what would I do? If I had 3 resistors instead of 3 capacitors, what would I do? In a series circuit, resistors are all solved the same way. What you would do if these were resistors, the first thing you do in any series circuit, and this is true only if you know all the values, all the R values. If this were resistors, you find RT, and then the second thing you do is you would use that RT to find the current. You say that current will equal the voltage over RT. That'll give you the current. And then the last thing you would do is you find all your voltage drops. Voltage across any resistor is the current from this step times whatever resistor we're talking about. You would do that for each resistor. Then the circuit's solved. Well, with capacitors, you do exactly the same thing. But just remember, we talk about current for resistors, we talk about charge for capacitors. So in capacitor circuits, what I would do is here I would find the total resistance. Here I want to find the total capacitance. And then we want to find the total current if I have resistors. Remember, we don't think about current for capacitors, we think about charge. So if I'm finding the total current here, in this step, I want to find the total charge. And then I can use that charge to find the voltage across each capacitor using the formula C equals Q on V. I can solve that for V and get all the voltages across each capacitor. What's true for both resistors and capacitors in any circuit is that Kirchhoff's voltage law must apply. If the voltage across all the resistors have to add up to the total, the voltage across each capacitor has to add up to the total voltage, and that can help us solve the problem. So given a problem, because if you look at that homework, you'll see series, you'll see parallel, and you'll see a combination of the two. And the student will go through this and get it, and they'll say, oh, okay, what if I add another parallel branch here? What would I do? Well, before this is over, we'll look at that. We won't work it out, but I'll give you some pointers. Let's go ahead and do this problem following this set of steps right here. So again, make sure you have pencil and paper. And let's do some calculating here. What I want to find for this circuit is the charge in the circuit for each capacitor, and I want to find the voltage across each capacitor. And I want to make sure that those voltage, I'll call them voltage drops, that they add up to the total voltage. So the first step we do is say, all right, if these were resistors, what would I do? The answer is I would find the total resistance. I would just add them up. But you got to remember, capacitors in series act like resistors in parallel, so I wouldn't add these up. What I would do is use a formula that's kind of similar to a parallel resistance formula. And since I have three, I'm not going to use the product over the sum. I'm going to use that reciprocal formula. So make sure you pen and paper out and go ahead and get your calculator and help me calculate. The formula I would use is the reciprocal formula, 1 over CT, that's what I'm looking for, is 1. Now I'm going to leave off the microfarads because I don't have a lot of room to write. I'm just going to put in the number. But we know if I put in the numbers, and our final answer will be in microfarad. I'm just going to, it's not a good idea to leave off units, but I'm going to leave them off on purpose here. This will be 0, 0, 2 microfarads. This would be 0, 0, 5 microfarads. And this is 0.1 microfarads. What I need for you to do is to figure out, remember I showed you how to use your reciprocal key. So I need to know what CT is. Give me the value for CT. Somebody. I guess I'll stick with the green. Okay, so calculate CT for me. 0.02, hit your reciprocal key, plus 0.05, hit your reciprocal key, plus 0.1, hit your reciprocal key, hit the equal sign, and then hit the reciprocal key one last time to solve for this ratio, and you should get an answer. Decimal answer. Does anybody have an answer for me? And I know it's 0 point something.
0.0125.
Okay, so 0.0125 microfarads. So I know my total capacitance is 0.0125 microfarads. Now, if you wanted to, the way to think about that is we basically combine all of these into one capacitor that has a value of 0.0125 microfarads. So the equivalent capacitance, if I combine all three, is this, and that equivalent capacitance is hooked across 80 volts. So in this equation that I'm working with, C equals Q on V. What I know so far, well, V they gave us, that was easy. That's 80 volts. You just solved for, somebody just gave me the answer for the total capacitance is 0.0125 microfarads. So that's over here. And all we have here to solve for is Q. So if you solve this for Q, then we got every three pieces in that equation we need. Now when you solve this for Q, leave this in microfarads. Just put in 0.0125. Don't take it out of micro. Don't write it with all of that. Because then our answer is going to be in, this is Q. Q is charge. Charge is in coulombs. So if you leave this in microfarads, since this is a whole unit of volts, our answer will be in microcoulombs. So somebody solve this for Q and tell me what you get for Q. So I got 80 times 0.0125 is what?
1 microcoulomb.
Okay, 1 microcoulomb. This right here is 1 microcoulomb. So what does that mean? Well, remember, we said charge for capacitors acts like current for resistors. In the series circuit of resistors, if I know the current anywhere, I know the current everywhere. What that means is a series circuit for capacitors, if I know the charge anywhere, I know the charge everywhere. Now, there's really no right or wrong way to do it, but what I usually do is just make this little squiggly thing like this and say, I'm going to call that charge. So this capacitor right here has 1 microcoulomb of charge. I just put this little cloud around it. And this has 1 microcoulomb of charge. And this has 1 microcoulomb of charge. If I know the charge anywhere for series capacitor connection, I know the charge everywhere. And that's kind of nice because now for every capacitor, I got the charge, I got the capacitance. The only thing I don't know is voltage, but I only have 3 variables. If I know 2 of the 3, I can get the third pretty easily. So we're almost there. This is not bad at all. So I'm gonna erase this. Well, you can go back and look at the video. I'm gonna erase it. I'm gonna say I was gonna pause, but just kind of notice that I'm using the same exact thinking that we would use if we had resistors. As long as you keep those couple principles we talked about in mind, that the fact that capacitors in series act like resistors in parallel and vice versa, and current is equal to charge when you deal with capacitors and vice versa, then this should be a piece of cake. So now what we got to do is find the voltage across C1, C2, and C3. And just like with resistors, we name a voltage drop across a resistor after the resistor. I'm going to name the voltage across the capacitor after the capacitor. So what I'm saying is, I guess this blue will show up. I'm going to call this V1. So we know that C equals Q on V. So that means that V equals Q on C. So I want V1, I want V2, and I want V3 using this equation. So I got Q. Now the charge is the same everywhere. So I might as well go ahead and put that in as 1 microcoulomb for all of these, because this is going to be the same for all of these. 1 microcoulomb, 1 microcoulomb. Now this is kind of nice because C for each of these is in microfarads, and that works out nice because then we just cancel out the micros. We don't have to worry about moving the decimal at all. So C1 is 0.02 microfarads. This is 0.05 microfarads. And this is 0.1 microfarad. So what I was saying was, since that's micro and that's micro, that makes my math really nice. I can just cross those out, and all I got to do is divide 1 by 0.02. What is 1 divided by 0.02?
50.
50 volts is correct. So I got 50. So what you want to do, just like you did when you had resistors, I asked you guys to get coloring pencils. So on your homework paper, what you will do, what you're going to submit to me, is you put your 50 volts right here. Now try to use coloring pencils, because if you save this as a PDF, I can actually see the colors and it's easier for me to grade. So I got 50 volts from here to here. And then what about this next one?
20.
20 volts is correct. So on the paper, you would show 20 volts from here to here. Now, for this one, you could do the same kind of thing. If you wanted to, you can divide, but look at this. I could say 1 divided by 0.1 is 10, but look at this. If this is 80, and this is 50, and that's 20, they add up to 70, Kirchhoff's voltage law applies whether I have resistors. No matter what I have, KVL always have to apply. So if I have a total of 80, and I got 50 and 20, I got 70 here, you don't even have to do that calculation. You know, this has to be 10 volts, and we're good to go. The circuit is solved. So these problems, if you did not struggle, if you understand, if you got good at doing resistors in series, resistors in parallel, and then the combination circuits, this should be a piece of cake. As long as you keep those principles that we discussed at the beginning of this lecture and the end of the last video. As long as you keep that in mind, then this will be pretty easy. That homework will be pretty easy. Okay? Now, I don't know if you have that sheet in front of you. If you do, I want you to look at that sheet. If you don't, I'm going to put it on the board. I want to show you. Because what happens, excuse me, on this sheet, you have 1, 2, 3, 4 series problems. We just did this one. So you got 3 more series problems just like this. But then they jump from series. They don't even give you a parallel. They jump right to series parallel. So I want to show you, I'm going to put the next problem on the board. I'm not going to work it, but we'll just talk about how you would solve it. So let me erase this. I'm going to put that next problem on the board, or one like it, and we'll look at the approach you would take to solve it. Anybody have any questions over any of the stuff that we did so far? Is that okay? All right. Well, if you have trouble, you can always send me a text. But I think this should be pretty easy. And there's a lot of other stuff on YouTube too where there are people going over this. This is pretty simple stuff here. But if you get confused, don't let that stop you from asking questions. So here is another problem from your sheet. I'm going down to like figure 518. And I might not get the numbers exactly right. I don't have my glasses on, but you'll get the point. So it looks like this. You got a capacitor here, 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 and then you got this. I might get my glasses cheap. This print is so small, I can't see anything. All right. So on this sheet, this is C1, C2, this is C4, and this is C3. They say that this is 2 microfarads. This is 1.5 microfarads. This one is 0.5 microfarads. And this is 1 microfarad. And they tell you that this is 25 volts. Again, I'm not going to work this out completely, but let's just figure out the approach we would take. Now think about what you would do if you had resistors instead of capacitors. If you had this, I gave you resistors instead of capacitors, like this. Maybe this is R1, R2, R3, and R4, and you knew the voltage. How would you solve this? Well, what you would do, you were taught to figure out your node connections, shade those in. So this is a node, that's a node. Maybe call 1A and 1B. Well, that's exactly what you would do over here. You would come over here and say, well, I got these in parallel. So that defines a node, and that defines a node. And then what you would do is you would redraw this, and we want to end up with a series circuit because everybody can solve a series circuit. So you say, all right, I got these in parallel. And for this one, to get the equivalent resistance, you say I got R2 by R3 over R2 plus R3, and you get the equivalent resistance. And then you would redraw this circuit. I got R1 here, I got R4 here, but this one you would replace with R2 parallel R3, which is whatever you got when you did that. That's REQ. And then you say, all right, my nodes are right here, A and B, and then you would go ahead and solve the circuit. You would find the voltages and the currents, and you would know that whatever voltage you got, when you found the voltage from here to here, when you found that voltage in this circuit, you know that voltage extends from A to B, But since that resistor came from these two in parallel, that means that both R2 and R3 get the same voltage. That's how you would solve this if you had resistors in series. You do this exactly the same way. It's done exactly the same way. Just like the goal here is to end up with a series circuit, the goal here is to end up with a series circuit of capacitors. So you would do exactly the same thing. The only difference is when we combine these two resistors, we use the parallel formula. Well, you're going to combine these two capacitors, and remember, capacitors in parallel act like resistors in series. So instead of using a formula like this, I'm just going to add these up. So long story short, what you'll do is you'll combine these, and you'll end up with the same circuit, but now it's a series circuit. So you got your voltage. That's C1. Now these two I'm going to combine into one capacitor. And then you got C4. This one right here is C1 in parallel with C3. But remember, parallel capacitors act like resistors in series, so I'm just going to add them up. I got 1.5 microfarads. I got 0.5 microfarads. The new value of this is going to be 2 microfarads. And then you know this is 2 microfarads. And then this was just 1 microfarads. And then I know that my nodes A and B are here and here. And once you get to this point, this is exactly like the first problem we did. This is the same thing. You solve this the same way, exactly the same way. The only difference is when you get all this solved, when you find the voltage across each of these, and you get the current, but the charge in each of these, then whatever charge you find here, you'll put here. Whatever charge you find here, you'll put here. And this is a very important point. The charge here that you get, you'll put here. The charge here that you get, you put here. But what about the charge here? This breaks up into two different capacitors. So you don't try to put the charge here. What you would do here is you found the voltage between these two capacitors. So you would find the voltage between A and B. And when you move that over here, that voltage is across both these capacitors. So now what you would know, since C equals Q on V, you would know C for this one is 0.5. You would know V, because you solve for V over here, so you would know this. The only thing you don't know is Q. So you can solve for Q for that one. And you can come over here and apply the same logic, use that same formula, solve for Q for that one. When you add those two Q's up, it should add up to whatever Q you got over here. The charge should add up. Charge is conserved. So hopefully that wasn't confusing. I think when you get into this, you'll see that as long as you can do your series parallel calculations with resistors, this stuff right here is a piece of cake. So we'll do that homework. I need to decide if I want to go any further with this. I mean, there's other stuff we can do with it. But we need to get back to the AC part because I know Russ has some labs he wants to do. Probably that's going to involve capacitors. I don't know. I'll see what he has lined up for you guys. Now, so I'm done. That's all I have. Does anybody have any questions for me over this or anything?
Yes.
Okay.
I just tried to submit the exam while we were in class, and I couldn't find a submission tab on Blackboard.
Okay. What I'll do in about, as soon as I'm done with this on Blackboard in the documents folder. But what I'll do is I'll put out an announcement with a link that will take you right to that submission tab. That way you don't have to look for it.
Okay. Thank you.
Anybody else have any questions or comments? Okay, well, if you do, I guess, guys, you know my number. You can text this. Well, I'm not going to put it up there. I'm going to put this on YouTube. But my number's on the syllabus. So if you want a fast response, just text that number. Or you can email me. I'll check my email. I just don't check it as often as I do the texting. So if you need to talk to me or you got a question, send me a text or shoot me an email, and we'll get it done. Guys, have a great rest of the day. Stay safe. And I won't talk to see. This is Wednesday. I won't see you guys till next Monday. So don't forget the exam. Make sure you put that exam up there before the tab expires. And I will talk to you guys on Monday.